welcome back. As we talked about last time, when we describe our data, we often want to indicate the spread of the data. We might indicate what is the range, what is the maximum, the minimum, what is the middle 50% of the data, the interquartile range. And so we talked about some of those last time. There are two other really important measures of spread, standard deviation and variance, and that's what we'll talk about today. Standard deviation and variance tells us about the dispersion of scores around the mean. Looking at this graph, we see that the scores are clustered somewhat close to that middle value of 6, and we're not using the endpoints going to 1 and 10. In comparison, this distribution uses each of those endpoints and is really kind of spread out a little bit more than that first graph. Variance and standard deviation gives us a way to numerically say how big that spread is, and it's something we almost always will report when we're describing a set of data that we have. Now, before we go too much further, I want to make a little note about things. We're going to look at numbers and formulas today. Don't worry, especially some of you who might be scared of math. Formulas can look scary at times, but, and this will be good for you humanities students out there, it's like learning a new language. You have to learn the vocabulary, and I'll translate those formulas, translating between the languages so that they'll make a bit more sense. Now, to start learning this new language, let's first look at our vocabulary list for the day. Now, we see here some symbols, and we'll work through these a little bit. Now, just like with English, it's an overall language, but it has different dialects and varieties. We also use a slightly different language if we're talking about samples, a subset of people, or the population, the entire group that we're interested in. And oftentimes we'll use regular letters for a sample, and we'll use Greek letters for a population. We'll come back to the population part in the future. Today we're going to talk about the sample column when we're describing a group of people that we have. Now, in the formulas that we talk about today, X indicates the raw score. With the bike example I talked about last time, the raw scores are the times of each, or the distances of each of my training rides. N indicates the number of scores. In the example, I had 20 different scores. Mean, we're going to notate that as either an M or what's called X bar. X bar is most common, except oftentimes we might use M because on the computer it's easier to write M than the little X bar, which is very hard to create. Then there's standard deviation, which we'll use S or something called S hat, and then variance is S squared or S hat squared. Now we'll walk through this and it'll start to make a bit more sense as we see what these terms actually mean. So now that we know a bit of the language, let's take a look at how we actually calculate the standard deviation and variance. Remember, don't get too caught up in the formulas themselves, but try to get a conceptual understanding of what we're doing. To make things more concrete, we'll continue using my bicycling example when I rode the 204 kilometers on the Great Ocean Road back in April 2015. Now, this graph here plots the 20 different training rides that I did, and it's just going across time from my first ride to my 20th ride. We see that generally I increased my distance over time, although there were a few points where I dropped down as part of my training as well. Now, as we did in session 3, we can calculate the mean of these numbers. We add them up, 69 plus 76 plus on through 179, divide that by 20, and this gives us an average distance of 108 kilometers, or about 109 kilometers if we round things. Now, if I return to this graph, I can draw the mean, 109, across this set of scores. And the mean in this case is a constant score that goes across all of those. Now, once I have this, we see that some of my rides were longer than the mean and some were shorter than the mean. And we can take each of those points and say, well, how far is it above or below the mean? That is, we're saying how much do each of these rides deviate from the mean value that I have. So I can look at one score and see how far that is from the mean. I can do this with another score and another score and another score. And if I average all of these values together, then we're going to get a sense of how much deviation or error there is overall across my different rides. So in other words, the standard deviation is essentially the average distance between each raw data point and the mean. Now, that's the conceptual part. The calculation of things gets a little bit trickier, and let's see why. First, let's calculate how much each training ride deviates from the mean. We take this by taking each raw score, noted here as x, and we subtract out the mean, in this case, which is labeled x bar. Now this chart does that for each of my training rides, and so we simply take x minus the mean of 109, and then we get the deviation. We see that some are below the mean, the negative values, and some are above the means, the positive values. Now, what happens if we take the average? If we sum all of these numbers up, we'll get 0. Try this yourself and see. And so we can't just sum these up and divide by 20 because we'd end up with 0, and yet we know that there is some deviation there. Now, we could take the absolute value of each of these numbers and take the average of that, but because stats like to make things confusing, we're going to make things a little bit more complicated in this case. So instead of taking the absolute value of each number, what we're actually going to do is square each value. So we take the raw score minus the sample mean, again that's the deviation score, and then we just square that, multiplying it by itself. Now here's the chart again, and now we have the deviation scores and then squaring that value. Now I'm just abbreviating deviation as dev just for convenience here. Now that I have those deviation scores squared, I can add all of those up. And so I just take 1016 plus 802 plus 444 on through the rest of the numbers. And in this case, we see the summed value is 17,460. And this actually gives me an indication of the overall error in my model. This actually has another name. So when we take those deviation scores, sum them all up, it's something called the sum of squares. We'll return to this when we talk about ANOVA, which is the reason why I mention this now. That weird symbol there is sigma, which just indicates sum up each of those squared deviation scores. And so we have the sum of squares. We calculate each deviation score, we square those, and then we add each of those up. And that's going to give me up the sum of squares. Now, the sum of squares does give me one indication of error or how much values are deviating from my mean, but the size of it really depends on the number of people that I have. So the more people I have, the larger the sum of squares is actually going to be. And I said I wanted to find the average deviation, not this squared sum value. So what we do is we divide by the number of people. So we're just taking the summed squared deviations adjusted by the number of people that I have in my sample. This gives us S squared. And going back to the formulas or the language that we talked about earlier, this is what we call the variance. And so the variance is those squared deviation scores summed up and adjusted by the number of people. Applying this to the data that we have, the sum of squares was 17,460. We divide that by the number, 20, and we get a variance of 873. So that's one indication of the deviation in my model. And we'll return to talking about variance a lot, especially when we talk about ANOVA towards the latter parts of these sessions. For now, one other measure to think about, and that's getting back to the standard deviation. Now, I said I wanted the average deviation, and the variance gives us an indication of things, but it's in squared units. And so it's hard to think about this average value that's squared. And if we go back to our language, our formulas, we can see here that the standard deviation is S and the variance is S squared. So this actually says that the standard deviation is simply going to be the square root of our variance. And so that's exactly what it is. We take our variance and then we just take the square root of that value, and that's going to give us the standard deviation. So once we have the variance, we simply take the square root of it. Returning again to our example, our variance was 873. We take the square root of that, and that's going to give us a standard deviation of 29.55. This just spells it out in a bit more detail. Here again, we see the distances of each of my ride, and there's the formula there to the right. And so we add up each of those scores, and or we take each score, subtract out the mean, and then we square it, and then we're going to add that to each of these deviation scores. And so that's going to give us, again, the sum of squares. We divide that by the number of observations, and this is our variance. And then we take the square root of this number, and this is the standard deviation. And so doing this, we see that across the 20 rides, my rides were 109 miles on, or kilometers on average, and the average deviation was 29.55 kilometers. Now it's your turn. Here's the set of scores that you had the past two times. Can you calculate the standard deviation and the variance? Here's the answers. Now, when you learn a new language, it helps a lot to practice. Same thing here. Along with the lecture, I've posted a link to practice problems. I'd encourage you to take some time and try these out. Then there's also an answer sheet so you can check out how you did. Now, hopefully this was not too painful an introduction to variance and standard deviation. They are two of the most important measures of spread that we use. We typically always report the mean, the minimum, maximum, and standard deviation. The variance we'll come back to, especially when we talk about ANOVA. Whether or not you understand the formulas and numbers does not matter so much. The key thing is to understand conceptually what we're doing and why. Thanks for listening. See you next time.